So this is picking up my voice. This is on now? I can't even tell. Okay. All right. That's all I need to do. What at the end of class? What do I do? Just
Down. If you have to go for some reason, just bring it to yourself.
okay. That works for me. All right. Thanks. So I'm going to pass around a sign-in sheet. It's in alphabetical order. If you don't see your name on there, just sign at the bottom of a sheet and see me afterwards. I just pulled that off of Blackboard, so you should have your name on there. And I'll pass back the rest of the exams after class. While we're waiting, if you could do me a favor and shut your phones off. There's really not going to be anything in your life that's more important than me for the next hour. And if there is, well, in the future, just let me know. Seriously, I really don't like these on during class because I find that even if you've got them on vibrate or silent, you're going to be tempted to be checking your text and emails and people text you and whatnot. So if you shut them off, that temptation goes away. But if there's something in your life that requires you not to be out of touch for the next hour, I understand. You can just let me know. And I would ask that you sit on the ends, and if you do have to respond to a text or something, just sneak out of the room and take care of that. Okay. I'm not sure, there's about 50 people in here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 4, 6... Well, that looks like about 50. So I'm going to get started. As I said, for those of you who just came in, there's a sign-in sheet being passed around. Just order. There's 3 pages to it, so look for your name, and if you don't see it at the bottom, I'll get it taken care of. We're going to be talking about derivatives. And I know Dr. Pillipackham, I believe Dr. Pillipackham was talking about derivatives during his last lecture. Is that correct? So I'm going to focus today on mechanics of materials and get into some other examples Wednesday and maybe a little bit next Monday, but then we're going to jump into some integration, I believe. So I'm in civil engineering. I'm actually in environmental engineering. And, you know, when you're designing a building, it's kind of nice to know, say, for example, how much deflection the beams are going to have before you put up the building. You don't want to put up a building to find out that your beam is sagging by 6 inches. You want to know how much sway there's going to be in a building. So if you remember when the link was first built, there were a lot of complaints by the patrons of that facility because, have you guys been down to the link? Or I'm not the link, is it the link or Citizens Bank Park? One. Who's, yeah, people were like, they've got these big towers of stairs, and people would be walking down the stairs after the game, and it's crowded, and the stairs are swaying and bouncing, and people were really, you can imagine, you're like 3 stories up, and the whole structure is bouncing as you're walking down, so people were getting really nervous. It was designed that way, but the people who were using it didn't understand that, and they were nervous. So the engineers knew how much sway and bounce they were expecting in that structure. If you don't know that before the thing is built, you might find yourself in a situation where your structure fails. I'm actually going to try and get... I didn't bring it. I thought I had a remote control. All right. So anyway, in order to figure out, for example, you're going to see in a structure before it's built, we're going to use derivatives. Oh, man. All right. Shoot. So here's an issue with technology. I started putting these slides together on my Surface tablet. And I thought I would do something, because it's a brand new tablet, I thought this would be cool. I can use my pen and write on my PowerPoint slides and save it. And when I look at it on my I see all of the drawings that I had up here, but they're not showing up on this slide. So I'm going to have to go through a couple of slides before I can get to the drawings. I will post these on the Blackboard site, and you can see the drawings that go with them. And in a couple of slides, you'll see some drawings because I changed over to the old style of PowerPoint. When you think about derivatives and why they're important, and I'm not sure exactly how much Dr. Pilipacum got into this, but if you're looking at the change in y with respect to x, how much elevation change is there over some given distance? That's the slope. That's the slope of a line. If you take the derivative of the slope, the change in the slope over some distance is defined as a moment. The change in the moment over some distance, the derivative of the moment with respect to distance, is the shear force. And the change in the shear force over some distance, the derivative of the shear force, is defined as the load. And again, you'll see all these figures. It'll be a little bit clearer when you look at these on Blackboard. So the derivatives can tell you all kinds of information about how that structure is going to behave. So here is where I decided my drawing skills are really bad, and this is why I went to using the old style PowerPoint. So in this case, we've got a cantilever beam. It's attached to the wall over on the left, and there is a load P over on the right. Look at that. There's a load P, and that load P induces some deflection in this beam. And in this case, we're told that the deflection is a function of the load, the modulus of elasticity, the EI is actually a function of the structural stability of the beam, and it's also a function of the distance you are along the beam as well as the total length of the beam. And if we know this relationship, we can figure out, before we ever apply that load, how much deflection there will be at this end of the beam and what the slope is over here by using derivatives. So that's what we're going to go through in this example. So, yes. That equation was given. So, can I go back? I guess I can't go back. So, in order to solve this problem, you need to know that equation. So that equation is going to be a function of the material. And it's a function of the material because of this EI. So this is our equation for deflection, and we're going to substitute the value L in to the equation in order to figure out what the deflection is at that point P. So this is just algebra at this point. This has got nothing to do with calculus. So if you want to know what the deflection is at this point where x equals L, you simply substitute L in where you have x, and it's P over 6EI L cubed times 3L cubed. Or minus 3L cubed, I'm sorry. Because in the original equation, it's 3 times L times x squared, and then we substitute L in. So it's 3 times L squared. So one of the things I try to do when I do my PowerPoints is put in every step so that you can see what's going on. So for some of you, you might feel like I'm taking too small steps, but if that's the case, just go with it. And for others, I want to make sure that you can see every step. So we simply then simplify this equation, and it becomes the deflection at L is equal to P over 6EI minus times negative 2L cubed. So whatever the length of the beam is, and whatever load you put on there, you can determine the deflection because the material that you have, whatever that beam is made out of, is going to define E and I. And that's something that will either be given to you or you can look up in a literature. Different kinds of steel have individual values of E and I, and you can put those in there and you can just look those up. You don't need to calculate them directly. All right? So this is how you can figure out the deflection. The slope is then simply the derivative of the deflection with respect to x. So here's our original equation. If we take the derivative of this equation, and slope is defined as theta. That's just a nomenclature for slope, just to use theta. And it's equal to the derivative of y with respect to x, and this is y. So the derivative of p over ci times x cubed minus 3lx squared with respect to x. So what's the derivative of p over 6ei with respect to x? How does p, 6e, or I change with x? It doesn't. So this is a constant. So we pull that out. What about L? Does that change with x? No. So we don't have to worry about that. Then we're looking at, and really, of x cubed minus 3L is a constant minus x squared. So what's the derivative of x cubed? 3x squared, and the derivative of x squared. Okay, right. So the derivative of x squared is 2x. 2x times 3L is 6. Okay. So now the slope x is equal to that equation, or is defined by that equation. So now we want to know out here at x, we'll substitute L in x. And we end up with 2EI, because I pulled the, let me just go back a slide and point that out. Here, this was P over 6EI, 3x squared minus 6LX. You can pull out 3, and this becomes P over 2EI, just straight algebra. Substitute L, and we end up with the slope is given as minus PL squared over 2EI. And again, P, E, and I are given or defined by the material, and L is the length of the beam. So the slope of the beam is defined by that function. Okay. You want to know this material, or you want to know how a certain material is going to function in the real world, we can use these derivatives to estimate what that's going to be. So, are there questions on that? Okay. So let's go through a couple more examples. In this case, it's a simply supported beam, meaning that at the ends, and it's free to deflect or deform in the middle. At this end where you see the triangle with the slash lines, that indicates it's a fixed connection. That connection cannot move. This connection over here with the, looks like a set of wheels underneath, that indicates that connection can move back and forth. So as the beam deflects down, this can move back and forth. This is fixed. And in this case, we're going to apply some load P right at the center point at a distance L over 2. And the deflection here is defined by this equation. In this case, P over 48 EI times 4x cubed minus 3lx L squared times x. And what we want to know here, this is kind of important. What's the maximum deflection you're going to get here? If you get a deflection of 4 inches, that's a really bad, that may be very bad. If you get a deflection of 1/10 of an inch, maybe that's okay. So we want to know what the maximum deflection is, and then the slope here at x equals 0, right at the end of the beam. What's the initial slope there? All right. So in order to get the maximum deflection, we've got to figure out the value of dy over dx at y max. What's the value here? So we want to know this maximum deflection. The deflection, in order to know that, in order to get that, we need to know the slope at that point. Why do we need to know the slope at that point? Yes?
Because at that point, the material's not bending anymore, so it's not changing.
Okay. What does that tell you?
That's the maximum amount that it can bend.
Okay. So what is this? How does the slope, knowing the slope, what's the relationship between the point of maximum deflection and the slope? It's going to be 0. Why is the slope going to be 0 there? That's right, right. So you've got a slope, if you start at L equals 0, or x equals 0, I'm sorry. As you move across the beam, the deflection has a negative slope here, right? As you get past L over 2, it's a positive slope. Well, it's got to go, to get from negative to positive, it's got to go through 0. So if we can find the place where dy dx equals 0, that's going to give us the point, the location for the maximum deflection. And even though it looks intuitive that if the load is a point load at L over 2, that's not necessarily always going to be the case for maximum deflection. So y max occurs where the slope is equal to 0, and it's located, the slope is dy dx, so take the derivative, this is y, take the derivative of that and set it equal to 0, and solve for x. Is there a question? When we take the derivative, again, p over 48e, derivative of 4x cubed, the derivative of x cubed is 3x squared. That's a typo. And the derivative of x is 1. This should be 12x squared minus 3l squared. Oh, I see what I did. I pulled the 3 out here. It's not a typo. This is why I try to do things in small steps, so that it becomes more obvious of what each step involves. So if we set this equal to 0 and solve for x, we can find the location where the maximum deflection is. And in this case, it's pretty straightforward. It's L over 2. So now that we know where the location is, we can go back to the original deflection equation and find out the maximum deflection. Yes? No, I had, this would be, if you bring this 3 back in there, you're going to end up with 12x squared minus 3l squared. Right? So all I pulled out was the 3, which left this 4x squared and 1l squared. Okay. So now we can go back to the deflection equation and solve for y max. And I just point out that, let me go back a couple slides. Because here, when you solve this, x could be plus or minus L over 2, right? And so you've got two answers, and you can have 1 point of maximum deflection. And in this case, minus L over 2 doesn't make sense because minus L over 2 is way over here someplace. You're not on the beam. So that can't be the right answer. So then the right answer has to be L over 2. So we put L over 2 into our deflection equation. 4 times L over 2 cubed minus 3L squared times L over 2. And simplify that. In this case, L cubed, 4 L over 2 cubed is L cubed over 8. 4 over 8 is 2. 3L squared over, this should be 3L cubed over 2. That could be a typo. Yeah, that's a typo. When we simplify it down to PL cubed over 48 EI. So we have our deflection equation. We take the derivative to find out where the location of the maximum deflection is. We use that location to determine what the value of the maximum deflection is. So are there questions on this? I mean, is this just like, just going through this, you know it all? How many people have read the textbook? Okay, so you've probably seen this before. This is right out of the textbook. So if you haven't read the textbook, it's new to you. And one thing, and I don't know what anyone else said to you, but I will tell you that to be successful in college, you've got to read the book before you come to class. Because otherwise, you're seeing stuff for the first time, and you don't even know enough to know what questions you have to ask. If you read the book before you come to class, you're going to find things that you don't understand, and then you'll be able to ask questions in class. So I would highly recommend that you do that reading ahead of time. Okay. So we now want to find the slope at this point, at x equals 0. So the slope is the derivative of y with respect to x. So we go back to our, the derivative of y with respect to x. Solve for that previously. We simply substitute x equals 0 into the equation, and we end up with 3p over 48 EI. X is 0, so 4 0 squared is 0 minus L squared. And it simplifies down to minus PL squared over 16 EI. So that's the, and again, P is given for any given load. E and I is given because of the material that you have, and depending on the material, they will change. And the length of the beam, you'll know that because it's part of your design. And so you can determine the slope at the 0 location here, the initial slope, using that equation. And you can do all of that before you actually build anything. Yes? Well, that was the question, was the slope at x equals 0, which is this point here. We could have easily found the slope at x equals L. The slope at x equals L is going to be? Same thing, well, opposite sign. It'll be positive. 4L squared minus L squared is 3L squared. And you'd end up with the same slope with a positive sign. Okay. So those were point loads. So we can do a similar process with a distributed load. You know, distributed load, if you look at the building that they just put up, and I don't know if anybody, you guys were up here at all over the summer and saw any of the structure that as it was being put up before they put the shell on it. But there's all kind, you know, the entire building is a series of I-beams stacked on top of each other, and they're done in such a way that the beams are taking distributed loads. So it's a simply supported beam. This end can move, this end is fixed. And in this case, a distributed load with a symbol, small q, q of x. And the deflection in this case is given by this equation. W naught, the length of the beam, EI, which is a function of the beam, and the sine of pi times x over L. So this is given to you. You need to know that equation before you can solve the problem. Derivatives. All right. So we want to find the slope. It's equal to dy dx. What's the derivative of this with respect to x? What's the derivative of this coefficient with respect to x? What's the derivative of the coefficient with respect to x? Yeah. You don't know. Hasn't answered yet. I saw your hand go up. Give it a shot. Take a wild guess. The coefficient of this. Just this fraction right here. W L4 over pi 4 EI. What happened to the W? So let me ask you this. Let me make the question a little simpler. W change with x? It doesn't. It's a constant, right? And L doesn't change with x, and neither does pi e or I. So this initial fraction is a constant. It doesn't change. So the derivative of this with respect to x is WL4 over pi 4 EI. So it doesn't change. So if we're going to take the derivative of this whole equation, the only thing we have to worry about. So what's the of a times x? You know the answer, don't you? Say that again?
It's cosine of the derivative side, if it's negative or positive.
Okay. So the sine of ax is equal to cosine x. Right. Cosine. So W L to the pi to the fourth EI up here. A times sine of ax. So the derivative of the sine of ax is minus a sine ax. So, and then and so this becomes WL cubed over pi cubed EI times the cosine of pi over x. So we can find the slope of this beam anywhere along its distance using this equation. All right. The moment, do you guys know what a moment is? So, and again, it'll be in my slides once I get them posted. So I'll draw it up here for right now. You have a beam, and you induce a load, you put a load on that beam, you've got a force pointing down, and let's say this is attached to a wall here. The force pointing down has to have a force acting in the opposite direction. So there's a shear force acting in the opposite direction. That force is also going to induce a moment. So that, think about it this way, the simple way to think about it, as the force pushes down, the object that's getting pushed on is going to try and bend back up. So it induces a moment. And that's what we're talking about here. So the moment is defined as EI times the second derivative of the deflection with respect to x, or the derivative of the slope. Well, we just determined the slope, the equation for slope, so we can use that equation here to determine and take the derivative of it and determine the moment. So d theta dx is the derivative. This is the equation for slope. So we're going to take the derivative of this. Again, W, L, pi, and EI are all constants. So we can just pull that outside the derivative. We don't have to worry about that. All we need to worry about is cosine pi x over L. So the derivative of the sine of AX is minus A cosine x. What's the derivative of the cosine of AX? Minus A sine. Minus A or plus A?
The derivative of sine is just A cosine AX. The negative was there.
Oh, okay.
What he said was right.
Okay, yeah, I guess I misread that as a negative sign. So let's, whoops, where am I at here? There we go. Okay, so the derivative then is minus A times sine of AX. And again, this is a constant. EI is a constant, and so the EI cancels. The pi will cancel one of those pi's. This L cancels one of those L's. And we end up with WL squared over pi squared times the sine of pi over LX. So now we've got an equation to determine the slope at any point. We've got an equation to determine the moment at any point. And then the question is, applied load. So essentially, a force that's trying to break that beam in half. So defined as the third derivative of y with respect to of the moment with respect to x. It's EI times the third derivative, I'm sorry. And this should be EI times d. So we go back to the equation of the moment, which is WL squared over pi squared sine pi x over L. The derivative of that. This is a constant. We go and we take the derivative then of the sine of AX, which is A times cosine AX. And we simplify it down to WL over pi times cosine pi x over L. And again, you'll see this in the slides when we post them. Find out the fourth derivative of y with respect to x. This is a way of checking your answer, because we're given this equation up here for load. We should be able to take the derivative of the shear force with respect to x and get that equation. Bless you. derivative of WL over pi times cosine pi x over L is equal to pi over L, the sine of pi over L times x, and the pi over, we end up back with our original equation. So, and this is another that you should learn now and not later. Learn it now. When you come to an answer, check it. Make sure it's right. Go back, check your units. Go back and make sure that the answer that you're coming up with makes sense. Don't just accept the calculations. Prove that they are in fact right. All right. Are there questions on that stuff? Is that pretty obvious to you? Doesn't make any sense at all? Somewhere in between?
Are you always going to find that initial like beam that you were talking about, and then not find the other one, the one that?
Let me go. Oh, you know what? No, it doesn't matter. So this is really beyond this course because are you in civil engineering? Okay, so you'll probably never see this. This is really a structural issue. There are that are designed with two fixed ends. There are beams that are defined with one fixed and one floating end. Sure, what would happen if you had two ends both floating? I'm not a structural engineer, but you can find the slope and the moment and the deflection at either end. The fact that one is fixed and the other's not is just part of this question. Other questions? Yes. It's negative because the load's pointing down. And if we go back, the shear force is acting opposite to the load. It's pointing. If you go back to the moment, it's pointing up. Other questions? All right. So that was really talking about how when you're looking at loads on a beam. We'll have situations where the loads are not pushing down, but they're pulling apart. They're even the building that we've got that just went up there, you've got vertical beams with beams connecting them, and there's going to be a load on those beams, a shear load, pulling them apart on the horizontal beams. So we really want to know how much load is on those beams and whether or not those beams are going to stretch or break. We want to make sure the beams are strong enough not to break or not to stretch. We can find the normal stress sigma as load P over the cross-sectional area over which it acts. So if you take the beam and you slice it, you can determine the cross-sectional area of the beam. So it's a point load acting on the center of the end of the beam. It is the shear stress over the entire cross-section. It's not just a point within the cross-section. Stress at something other than a vertical angle, right? So you can shear will induce shear stress along various angles. And we can use derivatives to figure out you put a strong enough force on anything, if you put force on it, it's going to break. And some things break along a vertical plane, and other things are going to break along something other than vertical, and what that angle is. So, in this case, body diagram, because we didn't really need it in the previous ones because it was a fairly simple analysis. In this case, we're dealing with various angles, so we can put together a free body diagram. We've got a force P acting horizontally, and we can break that force P into two components: a force acting along the plane and a force acting normal to the plane. And using trigonometry, we can define the force acting normal to the plane as P times the cosine of theta, and the force acting along the plane is V, shear force, which is P times the sine of theta. So if the stress is defined as the force over the area, then normal to the plane is the force F area, which is the cross area of the base, which is defined as the area of the beam divided by the cosine of theta. And we know the force is defined as, the force F is defined as the force P times the cosine of theta. A sub theta is A over cosine theta, and so the shear stress normal to this face is equal to the force P times cosine squared of theta divided by the cross-sectional area of the beam. The shear stress along the plane is equal to the force along the plane times the cross-sectional area. The force along the plane is defined as the force at the end of the beam, force P times the sine of theta. We can plug that in, plug in our expression for A sub theta. And the shear stress is then given as P times sine theta cosine theta times the cross-sectional area of the beam. Okay. So now that we know what these are, we can use derivatives and determine the maximum shear stress that will be induced by any given force. All right. So this is just a substitution of the shear stress, P over A, into these two equations. So the shear stress in the direction of theta is equal to the normal shear stress cosine squared. I'm sorry, this is the shear stress perpendicular to this plane, and the shear stress along the plane is equal to the normal shear stress sine theta cosine theta. So it just helps simplify the equations a little bit. Okay. So at some point, you're going to apply a force to the thing, and that beam is going to break. There's going to be a maximum value of the shear normal to the plane and a maximum value of shear along the plane. And those values are dependent only on the angle. So the question becomes, what is the value of theta at which sigma and tau are maximum? And if the value of theta is 0 for the maximum sigma and tau, when that beam breaks, it's going to break in a vertical plane. If the value of theta is something other than 0, then when that beam breaks, it's going to break at something other than vertical. All right. So we have till 12:50. Is that right? Okay. I think what I'm going to do is stop here and give out your exams because this is a good place to stop. So are there questions on any of this stuff? All right. So on Wednesday, I'm going to finish up example here, and I'll talk about, try and talk a couple of other examples of using derivatives and applying them. And then we'll get into integration next week. So, no questions, I'll call your name and pass out your exams.